Welcome to another exercise in a workbook statistics, this time focusing on t-test for coefficients and the f-test. Let's have a look at our exercise. Here we have, in the context of a market research study, you're asked by your boss to find out whether a relation exists between the age X and the time spent on consuming news Y. In the first pre-test, you collected the following data. And we have here our information. We have 5 participants, we have their ages, and we have the news consumption in minutes per day. Our first task then, determine the coefficients of the regression line that describes the relation between age and the duration of news consumption. And B, test whether the coefficients determined in part A are significantly different from 0 at an acceptable margin of error of 5%. Well, let's directly start with the first part, with the regression line and its coefficients. For this, I'm going to copy the table as is, and I'm going to add one additional column. This column I'm going to calculate the averages for X and for Y, giving me these two values. Additionally, I'm going to add 2 new rows to this table. The first row, I'm going to take all the X values and square them. So here 15 squared, 28 squared, 42 squared, 23 squared, and so forth. Again, for those numbers, I'm going to calculate the average. Then I'm going to finally add a second row, and the second row I'm going to calculate X times Y. So 15 times 5, 28 times 15, 42 times 20, and so forth. Again, I'm calculating the average. That's actually the only values I need here, those 4 averages. Because with those 4 averages, I can start with the slope parameter for my line. And I see here, first thing I need, the average of X times Y. That's the 489. Then I have to subtract the average of X times the average of Y. So 29 times 14. And divide all of this by the average of X squared. That's the 934.2 minus the average of X squared. So the 29 squared. This gives me as a final result 0.8906. This slope parameter I'm going to use to get then to my intercept A. Here I have the average of Y, which is 14, minus the slope of 0.8906 times the average of X, which is 29. This yields me an intercept of minus 11.8274. Taken together, they yield me the following regression line. That's actually an important first step because I need this regression line, not only the coefficients, but in general the information, to actually conduct a test on the coefficients. That's then the second part. I'm going to copy the regression line first, and I need in the first step the standard error of my regression. I can use this formula here, and I get this formula by taking my table and adding one additional row. This row I'm going to subtract from the Y values the Y hat values. Well, what is Y hat? Y hat is the value I get if I insert the X value into the regression line and then calculate a prognosis for Y. So I'm inserting 15, calculate Y hat for the 15. This Y hat I'm going to subtract from the actual Y value. So that's more or less the error between the actual value and the prognosed value. And this error I'm going to square. And that's what I get with these values. Those values I'm also going to take the, not the average of, but calculating the sum of. Because that's what I see in this formula. I need only the sum. I'm not needing the average at this point. I'm needing the sum of this squared difference, of these squared errors. And this sum I'm going to divide by n minus k minus 1. N was 5 observations. K I only have one x variable, one independent variable, so k is 1. So I'm going to divide this sum by 3. 5 minus 1 minus 1. That's the 66.8 something. And thereof, I'm going to take the square root, yielding me a standard error of the regression of 8.1735. With this error for the general regression, I can now calculate the standard errors for the two parameters, for the slope and for the intercept. So for the regression coefficients, same table as before, again with the sums, but I have to add something here. I have to add the row with the squared x values, and I need the sum thereof, and I need to calculate the square of each x value minus the average of x. Again, putting all these values here and taking the sum at the end. Why do I need this? Because for the intercept, the formula for the standard error is standard error of the regression times this part here. And I see up here, that's the sum of the squared x values. That's actually the 4,671 back here. Down here I have n times, so number of observations, times the sum of this difference, the squared difference I have here. So that's 5 times the 466. That was just the result from the previous slide. That's the standard error of the regression. So if I do this, I get a standard error for the intercept of 11.5727. Then I can do the same thing for the slope. Here the standard error is defined as standard error of the regression times square root of 1 divided by the sum of this last term. Well, here, therefore, under the square root, I get 1 divided by 466, and I multiply this with the standard error of the regression, yielding me in the end a standard error for the slope of 0.3786. So I have my two standard errors here. That's the only thing I need to conduct the test, because I already have the coefficients from the part A. So if I want to calculate my test statistics, the only thing I have to do is divide coefficient by standard error. And well, if the coefficient has been negative, I have to take the absolute thereof. So that's the corresponding test statistic for the intercept, and that's a corresponding test statistic for the slope. Then I can calculate my reference statistic. That's actually the value I'm going to compare this with. Here, the reference statistic is a t-statistic. So I'm looking up in the table for the t-distribution, the value t, n minus k minus 1, 1 minus 1 half alpha. Well, n minus k minus 1, we know this from before, is 3. 5 minus 1 minus 1. Alpha was 5%, so we're going to subtract 1 minus 1 half times 0.05, giving us 0.975. In the table for the t-distribution, we find therefore a value of 3.1824. This value we're going to compare with those two. So in the first case, we see the test statistic for the intercept is smaller. Thereby, we're going to retain our H0 hypothesis. We cannot argue that the coefficient is significantly different from 0. In the second part, for the slope, the same picture. Again, we cannot reject H0. We have to retain H0. The coefficient, again, is not significantly different from 0. So none of the two coefficients is actually significantly different from 0. So this usually is an indicator that we have a relatively bad regression going on. Or, well, in our case, we have very few observations, which might also lead to results like this. However, well, that's everything there is to this exercise, to this test. So I hope you enjoyed it. I say goodbye and see you next time.